Okay, let's go through a model example of a 2396 exam paper. This is one that we actually use on our online course as a mock, and one that can be done for all the learners to have a go, and then we do a session where we go through them, and there's a session for that. Thing to remember, this is a 3-hour exam, and it is a little bit long, and there are a lot of questions. It's actually broken into 2 parts though, sections A and B. Section A is the actual bit where you get quite calculation heavy, but section A is also only 30 minutes you're supposed to apply for it. As I was saying in the introduction, you're supposed to spend about 30 minutes on that, and then the 2.5 on the rest of the 8 questions, which are very much individual questions of different subjects, but they are mostly about your knowledge of the wiring regulations. So I'm going to go through this one. This paper is the one that we use on the online course, as I said. It's one that I deliberately don't regularly review. So a lot of these I need to kind of find the answers myself. I won't just know them straight away. I've got a clock coming up, which first of all I'll do 30 minutes, which is for section A. We'll see how close. I probably will overrun it, to be fair. It normally takes about 40 minutes. And then section B, we'll see how we go through. Alright, let's go. So, hit the timer, get that playing. 30 minutes for section A. So, new single-phase distribution circuit installed to a new board in a public house cellar. It will supply local lighting, walk-in fridge, standard ring final for pumps. Also suggested for 3 electric vehicle charging points and car park. This is all shown in the figure below. SP wiring armoured, limited to 70 degrees and an ambient temperature of 25 degrees. 400 volt supply, TNS 0.43 ZE, 1.8 KA, 100 amp BS88 system fuse E. I'm going to assume that main DB, that must be the fuse that protects this cable, I'd assume, to the cellar DB, and those are the circuits from there. Alright, so, first question, 1A, 1A. The installation reference method for the circuit, for this distribution, remember, see it says determine for the distribution circuit. That's what we're working on. That's what we're calculating to. So it says it's surface clipped. So that is reference method C. Now, that's from table 4A2. Now, you can go into the regs and find that if you're not too sure where that is. Best way to do that is to go to the beginning of appendix 4. I can load vital source up at this point, and you've got here a little list of all the tables. So we're looking at 4A2, and that is this one. Reference methods. Just find the reference method that matches. So we are looking for one that's clip direct, which is number 20. Number 20. You can see the description of it. It says fixed on a clipped direct to support, and that's reference method C. That's the one we'll use there. B, the applicable rating factors and their values. Alright, so the applicable rating factors, let's just jot those down. We have CA, CI, CC, CD, CS, CG, CF. Those are rating factors, but are they all applicable? So let's look at the scenario. Ambient temperature is CA. There's a mention of that being 25 degrees. Let's jot that down there. I, is there any mention of thermal insulation? Nope. It's surface clipped, so it's not buried in the ground. So there's no need for the CC, CD, or CS, because those are all about underground cable systems. There's no grouping described for the distribution cable, and the fuse will not be a 3036 semi-enclosure wireable. It's a BS88, so it's actually just a CA factor. So let's just delete all those ones. It's 25 degrees, so we're going to go to table 4B1 for that. So just get the regs up. B1, so we can just clip through these till we get to the end of it. Rating factors for ambient air temperature other than 30 degrees. 70 degrees thermoplastic, we're in that column there, and we're looking for 25, which is 1.03. Ca equals 1.03. That's the factor for that. Next we've got the table number and column from 7671 for the cable current carrying capacity and voltage drop. Now, this is worth 4 marks. We're looking for the numbers of the tables and the columns, so make sure you look at all the marks available. And it's asking for 2 things. So it's asking for the cable capacity, the cable current carrying capacity, if you will, and the voltage drop, tables and columns. So let's look for both of those, and they're basically next to each other anyway. Let's look in the regs again. Just pull. Get my regs up. There we go. We want to look at where all the cables are. So I'll scroll through Appendix 4. Now we're looking for here 41A, 42A, 42A. 42A is multi-core, but that's non-armoured. We want armoured, so we'll go to 44A. 44A, multi-core armoured 70-degree thermoplastic. Always read the titles of these tables very carefully. And we are reference method C, and we are single phase. So when you look at the titles here, you've got 2 core cables single phase, 3 or 4 3 phase. So we want column 2 for the cable rating. So that is table 4D4A, column 2. Now on the adjacent page, let me just get my mouse over there. There we go. The adjacent page, we have got the volt drop, which is 44B. But now look at the columns. Column 2 is for DC. We want column 3, which is the AC. So that is table 4D4B, column 3. And there's your 4 marks for that. Next, D. The minimum cross-sectional area, CSA, of the line conductor for the current carrying capacity. So, D. This is looking for the IZ. And the size of cable is the answer for the IZ. But to get IZ, we first of all have to calculate IT. And IT must be greater or equal to IN over CA. This is basically using equation 1 from Appendix 4. Now, if you're not familiar with where that is, again, I recommend you go to the beginning of Appendix 4 and you just read Appendix 4 through, and you'll see all the design bits that you need. One sec. Alright. Sorry, I just had to put the dog away. A distraction you shouldn't be having, that's for sure. So, let's get the regs open. Ambient temperature told. We want to get through these first few pages of Appendix 4, and there's this bit here where we have the equations. And we're looking here at equation 1. Because it's equation 1 because we've identified there's no grouping. So single circuit is equation 1, IT is greater than IN over, and the only factor we have is CA. So that is just going to be then 100 over 1.03. So make that disappear a moment. Get the calculator up. $100 over 1.03, 97 will do. We could be a bit picky with that, but 97 amp. Now we need to go back to table 4D4, column 2, which we just said in our previous question. So I'll just do that in the regs, which was page 454, I think. Yeah. So we're back on this page, 454, for table 4D4. And we are column 2, and we want to find the next number over 97, which is 118, which belongs to 25 mil. And that's actually the answer to the question. So 25 mil, 118 amp is the cable current carrying capacity. The question is the minimum cross-sectional area, CSA, of the line conductor for current carrying capacity. The answer to that is 25. E. The maximum volt drop allowable for the distribution circuit. Okay, so one thing to address there is this is a distribution circuit. So when you think of volt drop, you might think, oh yeah, volt drop. Well, 5% for other circuits and 3% for lighting if they're on a public supply, which this is. But that's from the point of origin to the end. And we're doing a distribution circuit, so we don't want to use that. We need to have a deduction, but we need to remember that there is a light circuit, and whilst the light circuit itself probably won't have any near a 3% or a 6.9 volt drop, we need to give it some consideration. So a rough ballpark here of this 3% is to shave off and allow for 1% or 2% off of that. So I mean, just to address this, if we were to think about, we're putting in a board here, in a circuit which feeds a board here, and there's going to be a light circuit off of it there. Now, from here to here, that length is 3%, or 6.9 volts. But if we put a 3% volt drop from here to here, because that's the circuit we're installing, we're giving nothing left over for this light circuit itself. So instead we need to say, well, let's not do 3%, let's go with something less. So let's go with 1% or 2%, that leaves the remaining 1% or 2% over for that light circuit. Now a light circuit these days is all going to be LED driven, and if you think about volt drop being IB as one of the main culprits of that design, I would confidently say we could have a 2% volt drop for the distribution circuit and then 1% for the light, for the total of 3%. I'd be happy to do that because I'm pretty confident that the LED power demand would be very negligible, and if we restrict ourselves to a 1% volt drop, we might find the 25 mil is too small. So let's go with this idea of a 2% allowance. So the volt drop for this circuit equals 2%. Now 2% of a single phase circuit, so 2% of 230, well, that's basically 1% is 2.3, so 2% equals 4.6 volts. That we're going to say is the maximum volt drop allowable for this distribution circuit. Alright? So what they're doing there in the exam is they're seeing if you can determine that distribution circuits should have a volt drop, but they should not take all of the volt drop allowable, and we should have some volt drop remaining for the circuits on the actual other end, because if we take all of it, then there's going to be no room for the final circuits themselves. You could by all means try 1%. I have a feeling that 1% might be too much for a 25 mil of 23 meters. So I'm going to go with 2%. This obviously will leave 1% for lighting. It will leave 3% for others, and the lengths of the EV chargers and the other circuits. We just don't have that data to kind of work with that. So I'm going to go.
Sorry, I don't know that.
I'm going to go with this as an approximation. So, the maximum volt drop allowable for the distribution circuit, I'm going to say is 4.6 volts, 2%. The next question then is the minimum CSA to achieve that volt drop. So what I now need to do is transpose the volt drop formula so that the volt drop times 1000 over the design current times the length is equal to the millivolt per amp per meter. Therefore, the 4.6 is 4,600 over the 100 times 23. Let me just verify it was 23. Yeah, 23 meters distribution. So I'm going to do that on my phone because I can't use brackets on the Windows thing without messing it up. So 4,600 over bracket 100 times 23. Well, 2,300, isn't it? Equals 2. That equals a maximum of 2 millivolt per amp per meter. Now what we want to do is return to 7671 and we want to go to the adjacent page, column 3, which was for our cable. We want to find the next number that is 2 or less. So you can see a 16 is 2.8, whilst a 25, just considering impedance at this point, is 1.75. 1.75. So the 25 works here. So 1.75 millivolt equals 25 mil. Now, just to kind of play devil's advocate, with the idea of 1%, let's see what 1% would have got us. 1%. So 1% would have been 2.3. That would have been 2,300 over 2,300. So that would have been 1, wouldn't it? So if we did 1%, we'd have had 1 millivolt. 1 millivolt would have made us have to go up to... We'd have had to... Well, yeah, we'd have had to go up to 50 mil. Had we gone with 1% volt drop maximum, we'd have gone up to 50 mil in size. So it was the right decision to give us a 2% volt drop of 4.6. So back to question F. Minimum CSA for the volt drop. For the volt drop alone is 25 mil. We've already worked out for thermal that our cable size needed is 25 mil as well. So we're pretty good now with a sizing of 25 mil here. Minimum CSA for the volt drop. We can actually verify the volt drop is there. That's done. The actual circuit's volt drop now is G. So the actual volt drop is the millivolt per amp per meter times IB times length over 1,000, which is 1.75 times 100 times 23 over 1,000 equals 1.75 times 100 amps times 23 meters equals over 1,000 equals 4.025 volts. So that 4.025 volts is the actual volt drop, and the maximum we said we could have was 4.6. So we are within. So that's our actual volt drop of our distribution circuit there. So if we think about a light circuit, that would be 6.9 minus 4.025, which gives us, you know, nearly 3 volts. So that's pretty reasonable for a light circuit with very low power. So it's not too bad. Right, that gives us, we are at 12 minutes remaining, and that is 1 done. We move on to 2. So we've got a size of line conductor of 25 mil. And let's go with blue. We'll go on to number 2. 2A. Let's scroll this up a little bit. Oh, too far. Okay. Determine a distribution circuit, the minimum permissible CSA for the CPC to meet the maximum ZS requirements. Now, it's worth 6 marks. There's a few little things to work out. So the first thing we need to work out, well, what is... Oh, hang on. There we go. 2A. What is the minimum permissible CSA for the CPC to meet the maximum ZS? So what is the maximum ZS? The maximum ZS is equal, well, this is a 100 amp, and it's a BS88, and I believe it was a fuse system E. Yeah, so fuse system E. So for that, we want to go again to 7671. You can go to part 4. protection against electric shock. In there, a couple of pages in, we'll have the tables. And we are looking at a distribution circuit, so it's clearly 5 seconds disconnection time, which is table 41.4. Alright. Note that in your answers as well, so that the marker knows where you went. Fuse system E, BSATH2 100 is 0.42. Maximum ZS. 0.42 ohms, table 41.4. 0.42 ohms. What do we do next with that? We want the minimum CSA for the CPC to meet the maximum ZS requirements. So what we want to do is work out the ZS, then deduct the ZE from the ZS. So ZS minus ZE equals R1, R2, theoretically anyway. Alright, we're not delving into reactants here for some reason, because it's only worth 6 marks. We haven't got the space for it. So the ZE for this is 0.43. So we have a 0.42 minus a 0.43. Well, that immediately is a problem, because it kind of tells us that our ZE is too high. So this gives us this interesting scenario where we have a ZE that's either too high for us just to do calculations, or we need to change something. So what's been suggested on the courses before is, well, the only thing we can do really is reduce the device, so we can change that 100 amp down to 80 at this point. Although we've gone with that as an IN for our design, we can at this point select it downward, and we can then work on the ZS of that, and the ZS of that being 0.55, which gives us a little bit of room for improvement. Fundamentally, sometimes you will get errors in papers, and you need to, and I remember this when I did my old 2931-20, which was one of the old design course numbers. If you're not sure what to do, because you think, oh, this can't be right, all you can do is add a comment. So you can comment saying suggested solution, because you have to kind of keep moving forward with the calculations. If there is an error, and there was a typo in the paper from last December, there was typos and all sorts, so errors do creep in. But if you get an error like this, we can just go, okay, well, let's carry on moving forward with the design anyway, so the person marking it can see our design ability here. We've identified then that the maximum ZS of a 100 amp BS88E is higher than the ZE has given us. Is lower than the ZE has given us, which is a non-starter. We'd have to change our earthing system, we'd have to improve things, get more of a required bit of data from the supply, or we could change our circuit characteristics so that it works, and that's what we're going to do here, because that's what we can do from a desk study version. So we're going to just drop it down and work with a suggestion of using an 80 amp instead of the 100 amps fuse at this point. This gives us a ZS of 0.55 and a ZE of this. So if we write this again, ZS minus ZE will therefore equal 0.55 minus the 0.43, which gives us a 0.12 space to work for our R1 plus R2. Okay. Again, as long as you're happy that you have identified a potential issue with the paper, you can carry on moving through. It has happened in the past, so it's a good experience to kind of see this here now. The question again, 2A, is minimum permissible CSA for the CPC to meet the required ZS. So we want to work out what the R1 is. R1 is equal to 23 meters of 25 mil. Okay, and we want to obviously look at the resistivity of this. Now you can find this in your on-site guide, in your guidance notes, and trying to remember which books. I think those are the only other two books you can have. You can't have the IET design guides. You can look at them in there. Fundamentally, the resistivities are not in BS 7671 of the conductors. So you'd have to get the resistivity of R1 from one of those books, of which I don't know if I have one within reach. Oh, I do. Hang on. Oh, gosh. What's that one? I've got the on-site guide. It's unusual for me. So let's just hide the regs for now. We don't need the regs. We're not in the regs. So we are finding the resistivity of R1 for 25mm, which is in the on-site guide on page 218. Our 25mm line conductor on its own is 0.727 milliohms. $25mm equals 0.727 milliohms per meter, millimeters. Therefore, 23 times 0.727 times. Excuse me, I have to sneeze. Hang on. Right, times 1.2. And the point of the 1.2 is the 0.727 value is given at 20 degrees, and we want to work out its resistance at 70 degrees when it's at operating temperature. And we're going to do that over 1,000 to turn it from milliohms to ohms. So again, 23 meters of 0.727, which is 25mm resistance, times 1.2 to get it up to 70 degrees, over 1,000 to get it into ohms, is 0.02. So the resistance of 25mm for 23 meters is 0.02 ohms. 0.02 ohms. That's a very bad ohm symbol. There we go. Now, if we have maximum R1, R2 equals 0.12, and R1 of that equals 0.02, therefore R2 will equal up to 0.1 ohm. So what we need to do now is turn this R2 resistance into its R2 resistivity. So we take this R2 that we have, and what we want to do is we want to take R2 and we want to go, okay, 0.1 R2. If we then times that by 1,000 and then divide that by the 1.2 temperature correction by the 23 meters of length, this will give us a 3.623 value, 3.623, and this is what we call the R2 resistivity. So now we want to look at the conductors and find a resistivity that is that value, or something that has less. We don't want any more resistance than that. So 1 mil is 18.10, too small. 1.525 is 7.4, too small. 4 mil is 4.61, too small. 6 mil is 3.08, that is underneath. 10 mil is 1.83, so 6 mil equals a 3.08 resistivity, milliohm resistivity. So the answer is the minimum permissible CSA for the CPC to meet this maximum ZS is 6 mil. Now there's another way you can work that out, which I'll just cover now, even though we're going to run out of time for this little bit. And that is that you could say, well, the R1 plus R2 what you have, which in our case was 0.12, times 1,000 is a higher value over the need to have the correction rating times its length, which is basically 0.12 times 1,000 over this 1.2 times 23 meters equals. So I'll quickly do this. Just as another example, 0.2 times 1000 equals 120 over 1.2 times 23 equals 4.347. And that's your resistivity of your combined conductors. So 4.3478. So let's call it 348 milliohms per meter resistivity. Now if we deduct from that the 25 mil that we had earlier, so let's take away the 0.727. If we take away 0.727, take away 0.727 milliohms for the 25 mil, that will equal us with 3.62 milliohms, which is where we were there. So there's two ways to work out that, and then with that you select the conductor that has a lower resistance, which is 3.08 for 6 mil, and that is the answer to 2A. Alright, now we know we can have this. Remember, whilst you're going with an army, do you think, well, it won't be a 6 mil, it won't be a 6 mil? It doesn't matter. The question is the minimum permissible CSA for the CPC to meet the maximum ZS. That's what the question's asking you, not what cable would you put in the wall, okay? So B. So obviously I've ran out of time for this half an hour, but we'll just do B and C because I've obviously had a couple little pauses on that. B. The design ZS, so ZS is equal to ZE plus R1 plus R2. And we know therefore that ZE is equal to 0.43 in the scenario. Plus our actual R1, R2. So if we have an R1, R2 that incorporates a... In fact, we haven't actually calculated the R1, R2, I don't think, the actual one in there. So let's calculate the R1, R2 in this question. So the R1, R2 is equal to the resistivity of 0.727 plus 3.08 times 1.2 times 23 over 1000. So the R1, R2 will equal... I realise I'm right behind my head now, so I'm just sliding it down slightly. There we go. Alright. Not bracket 0.727 plus 3.08 close bracket times 1.2 times 23 over 1000. 0.105 equals 0.105 okay, so basically yeah, it's 0.105073, so you could push it up to 0.11 ohms if you wanted to. Okay, now the maximum we were allowed was 0.12 with this adjustment that we had up here, way up here. Here the maximum was 0.12, and we've actually then got our design in, and we've got an actual of 0.11. We'll add that to the ZE, which gives us 0.54 ohms, and the maximum ZS was 0.55 when we switched it to ATM. So the design ZS is 0.54 ohms. C. Suitability of the CPC for thermal constraints. So what we need to do there is consider the adiabatic is I squared T over K. So what we want to do here is find the K factor. So let's find the K factor. And the K factor is, where's my regs button? Right. Oh. There it is. Right, so we're going to go along with the idea here that again, we're going to go along with the idea that our conductors are 3-core armor, and we're just, in this case, we're just going to concentrate on it being an included conductor here for the CPC, mainly because if we start using the armoring, we have to get more tables, we use reactants, and that's just not in the books that you have in the design course for some stupid reason. You don't have the IT design guide with all those other resources. You have limited books, so we don't do that. So we're just going to work on a additional protective conductor for this one. So we're going to go to 54, chapter 54. And in here there's the adiabatic equation, sizing of protective conductors, and on the adiabatic, then you've got the next page, page 200. Now in this case we're going to use that common factor of 115 because we are keeping it incorporated in the cable bunch and we're not going to run it as a separate one. If you were doing an armor as the actual protective conductor, then you go to this table below where it's 51 for steel. Okay, so do pay attention to that. But for our case, we'll go with 115. So I squared T over K. K is 115. Now, how do we determine I? This is where, again, it depends on how well your kind of coverage has been with design, how deep it's gone. But fundamentally, when we come to determining things, we have to decide if we're going to use 230 volts for single phase, or if we're going to go with a C min, which is 218.5, or a C max, which is 253, to do with the variations in the supply voltage. We do 218.5 when we're trying to determine disconnection times, if disconnection times will be achieved. So we work on the C min to determine the lowest potential fault current, which will establish us the longest disconnection times. Here we're working on thermal withstand, so we want to determine the maximum amount of current that could be expected. So I'm going to use C max of 253 over the ZS we just determined of 0.54 to give me a prospective fault current for this circuit. Now, to bear in mind, we are really just working here on prospective earth fault current, okay, so bear that in mind as well. But that's why the question is asking for, I can go back to there now, the suitability of the CPC for thermal constraint. And that's why we're working on this 0.54 ZS. If we were working on the thermal constraint for short circuit, you'd have to take the R1 conductor and then basically kind of double it all, because an RN or another phase would be the same resistivities. Alright, so that's 468 amps. So 469 amps, 469 amps, so that's going to be 469. Logically, we would expect that that would achieve disconnection, but we can interpret that it will, because obviously it's over the ZS. But we can have a look at what kind of time that's going to take. So what we want to do is we want to figure out what time 469 will disconnect this device. This means going to Appendix 3. So it's, again, so important that you understand how to navigate and use the regs. And we're going to go to Appendix 3. And we're going to go to our BS88 fuse system E bolted curve. That's not the curve. That was the wrong thing to click. Oh, I thought I had an easy quick reference. I have to do it the old-fashioned way of clicking forward. Alright, fuse system C, 3036, 3036, fuse system E, 80 amps on here. So what we want to do is we want to figure out, we have 469, so 100 is here, 200, 300, 400, and then we're going to go halfway and a little bit more up until we hit the 80, which is about there, and then, so that's 400, 5, so about there, so in between 2 and 3 seconds. Let's go again, 1, 2, 3, 4, 5, about here. Yeah, we're in between 2 to 3 seconds. So that's, in this case, we're looking for the length of time. So let's say that the fault could be there for 3 seconds. Is a bit of a worst case. 3 seconds. And don't forget to square that. Okay, so just put 3 seconds in there. 469 square times 3 equals square root over 115. 7.08 0.06 mil. Millimeters. So that's actually going to be a 10 mil. So that needs to be 10 mil. So the answer to C is going to be the suggested 6 mil is not suitable, and you recommend 10. Okay. Yeah, because we switched to 280 amp here, and we had a 25 mil line, and we had a 6 mil CPC, and the amount of current that will achieve not suitable for the duration of time. And this is one of the things with distribution circuits. We can sometimes have to size them because of those disconnection times that they all have. Because the ZS there was enough to achieve a 5-second disconnection. So yeah, that would not be suitable. Good. What's next then? Actually, that wraps up section A. So the last bit here kind of shows why it is so important to do these calculations and do these checks. The fact that it was a distribution circuit, the fact the ZS's weren't so low, and that the duration of the fault time and clearance time was a bit longer than the normal 0.1 that we're so used to, just addresses how important it is to work out these calculations. Good. Now that wraps up A. We were probably about 10 or 15 minutes over. I did say it take about 40 odd minutes. So let me just pause this and I'll get a clock ready for another 90 minutes, which I think we'll do in another little video just to kind of break this up into 2 points. It's a process of the same kind of question structure. Okay, get the scenario, reference method, the factors applicable, then tell the marker where you're looking in the book. What table am I looking at? What number for this cable type? What column for my cable information? And then when you've got that, you work out what the IT is to select the IZ, which gives you the cable size. Always look at what the question is, though. It's asking for the size. So don't just give a amps answer. Make sure you get the size, you get the answer they're looking for. It's a very easy way to lose marks by not actually giving what has been asked for in the question. We can easily get distracted with so many other things in our designs here. We then had to choose how much volt drop we would allow, and we went for a distribution circuit. We made some presumptions of 2% instead of 1%, and actually worked out in our favour for the 25 mil. And when we determined that it would be suitable for 25 mil, and the volt drop would just be 4.025 volts, that finished the first section. The second section was all about ZS and earthing and actually disconnection, the ADS in principle. So we had to calculate the size CPC for the maximum Z requirements. That's worth 6 marks because there is a little bit of working out to do. First, we actually have to work out what the R1 and the R2 and etc. should be to then determine what the actual ZS should be. Then we have to kind of reverse engineer it. Then we have to work out the design ZS, and then we had to actually work out the thermal withstand. So there's quite a few little things to work on there. It can get a little bit challenging when you're working with resistivities and you're working with factors. Always just try to make sure you know when you're putting in your temperature changes, going from 20 up to 70 or 70 down to 20. You know, the multiplying by 0.8 gets us from 70 down to 20. By multiplying it by 1.2 gets us from 20 up to 70. Divided by 1.2 is the same as multiplying by 1.8 and 0.8, which gets us the other way around. So there's all sorts of ways to do it in transposition. Just practice, and you'll be fine. Alright, let's move this on to the next one on section B, which is going to be 90 minutes to go through section B.